gonna change over to writing mode. So you get to see me like this, like, I really like it. It looks cool. Do you see how like I'm in the corner? It's like I'm a really bad Twitch streamer. Anyways, so let's talk about approximating areas. So one of the things that we do in calculus a lot of the time, like one of the major questions of what we work on, is figuring out the area under a curve. So let's talk about that. Okay, why is it not letting me insert this? Boom. Okay, there we go. Okay, I want to move that. Please move it over. There we go. Okay, so here we have like our x and y axis. Here we have a function, our f of x. And let's say we have two x values. So over here we have x equals a. Over here we have x equals b. And what we're interested in doing is figuring out the area of this region here. Okay, so let's come up with a written description of that region. So the region is 1. First of all, it is under f of x. Right? The green area is under the curve f of x. 2, it is above the x-axis. Right? You're just looking at it, you can see you're below the red line and above the axis. 3, it is between x equals a and x equals b. Another way that we would say this is we would say that is in the interval AB, or on the interval AB. So if we talk about being between x equals a and x equals b, you could also describe that as in the interval AB. Right? So like you have those vertical lines, x equals a and x equals b, the horizontal line, which is the axis, and then your curved line on top. You want everything in meeting those 3 criteria. Hopefully your 101A class last semester got to this. They don't always, so we're going to cover it just in case. Now, let's talk about when you don't need to approximate the area, when you can just figure it out. Okay, so there's our graph, our axes. X-axis, y-axis, and let's put in a line. So let's say that's our f of x. And again, we have x equals a, x equals b. Okay, so we want that region there. Looks like this. Oh, this is one of the best investments I made during the pandemic. Does everyone see my cool writing board? It is so much better. Have you had professors that use like the mouse to try to draw all of this, or have people everyone's gotten this? Okay, good. I was like worried at first because I know for the longest time people like hadn't, and I was like, holy shit, how are people doing this? I like struggled with it for a couple months before I finally cave in. Okay, so but looking at this, with this particular shape, you can split it up into 2 parts. So you get this first part right here, which is a rectangle. We'll call it part 1. And then you get this other part over here, which is a right triangle. Call that part 2. And looking at them, you can figure out the area under the curve pretty easily. The area of 1, because it's a rectangle, that's just going to be the base times the height. The base is just b minus a. Right? The distance between a and b is b minus a. And then the height would be determined by f of a. So why did I put parentheses? Yeah. Yeah. That's for a triangle. I'm talking about 1, which is a rectangle. But good catch if it was the other one. So now we can talk about, well, the area of 2. For a triangle, that's 1/2 of base times height. Looking at this, the base is, again, b minus a. Now the height is this part right here. Notice you can take the big height, which is f of b, and subtract the small height, which is f of a, leaving you with the height that you actually want. So looking at this, like if you wanted to find out this area, it's not that hard. You would just plug the numbers into this formula, add them together, and boom, you get this area. Now, the only reason that you can do this is because you have f of x is a line, or it's linear, however you want to describe it. And because there's a line there, it gets split up perfectly into a rectangle and a triangle, yes? In the example above, that doesn't really happen. You can draw a line right here and you get this rectangle piece, which we can call area 1. But then area 2, if you look at it, it's like, I don't even know how to describe this stuff right here. It looks like a door wedge or something, right? Do you see how it's like, it has a flat bottom, a flat side, and then this curvy top. There's no nice ready-made formula to calculate that, right? It's only because you have that flat top that you can split it into 2 parts and figure out what the area is. So you have this real problem when that top curve is not linear, if it's got any sort of smoothness to it. So what we want to do is we want to figure out, like, well, how would we figure out this area? Like, we can't break it up into elementary shapes, so what are we going to do? So the solution that we have is that we approximate the area instead of calculating the correct answer. Okay, that's what we're going to start with. We're going to say, like, okay, I get it. It's curved on the top. I have no formula just to do that. Instead, what are we going to do? We're going to try to approximate the area. There we go. So let's talk about how we do that. So let me insert, oops. I wanted an axis again, but it keeps on disappearing when I try to do it. There we go. So here's our axis. Let's draw in our function. Okay, there we go. And again, we have our x values a and b, which are called our left and right bounds. I will write that down in a second. So a and b are the left and right bounds. Comes from the fact that it's the boundary of the area that you want. Okay, so what we're going to do is this interval between A and B, down here, which I just squiggled in blue, that's an interval. An interval. What we're going to do is partition it. We are going to partition the interval. What do we mean by partitioning the interval? We're going to break it up into equally sized pieces. Okay. So usually you're going to determine ahead of time how many pieces you're going to break it up into. Let's choose 4. So n is always the variable which tells you how many pieces you're going to break it up into, or partition. What the hell's going on? It's like out of nowhere there's a bunch of notifications happening. Uh-oh. Sorry, I just need to silence that. It's getting really annoying. There we go. Thank God. There we go. Okay. So you need to determine ahead of time how many pieces you'll break the interval into. So we're going to break it up into 4 pieces. So if you break it up into 4 pieces, you take your interval and you first split it in half, which is why I'm writing a blue line right there in the middle, and then you take each of the halves and you split them in half. Right? So you get 4 pieces, equally sized. Now, so we're going to call the width of each of these pieces delta x. So delta x, delta is that triangle. So delta x means the width of each of the individual pieces. It's delta x because we're partitioning along the x-axis, right? A to B is along the x-axis. Okay, so each of those equally sized intervals is going to be the whole interval, which has a width b minus a. And then you have to divide it by n, the number of pieces you're breaking it up into. So this is the formula you always use to figure out how wide each of your pieces will be. So you're going to have 4 things, each of length delta x, where delta x is b minus a over 4 in this case. Okay, so then what you're going to do, so I guess really the way you should think about this is you have a point right here, a point right here, a point right here, a point right here, and a point right here, and they're all equally spaced delta x apart. So you're going to use those points to make rectangles. So you're going to have a base for each rectangle. Your base will be from that point to that point right here. And then a point from here to here. Hopefully you can see me sort of like drawing in the bottoms. Like, do you see how first there was blue right here, and then green, and then red? Those are the bases of each of your rectangles. Okay, so now what you have to do is you have to choose how tall your rectangles will be. Usually what you do is you're going to use the left or right endpoint of those bases to determine the height. So let's say that you use the left point. It means you look at this base right here, and what you do is you take the left endpoint, which is the one right there, and that will determine how tall your rectangle is. So that left endpoint ends up right here on the function, and you get a rectangle that looks like this. Okay, so that rectangle has a width of delta x and a height of something which I'm just going to call f of x. And then you keep doing that for all the different rectangles. You move on to the next base. The left endpoint is this one now, and you'll get a rectangle that looks like this. You go on to the next base. The left endpoint's this one right here. I'm not doing a very good job of drawing it, but you can see that you get a rectangle. And then you take the next base, the left endpoint is that one right there. You get a rectangle that looks like this. So it's sort of like draw these in here. Here's one rectangle. Here's another rectangle. Here is another rectangle. And here is another rectangle. And let's zoom in a little. A lot, actually. It's pretty cool because you can't do this on the board in like real life, right? And it'll just like zoom in. Okay, if you look, this is an approximation because if you look at this rectangle right here, do you see how some of the rectangle goes past the area that we actually want to calculate because we only want the area under the curve? So this is called a overestimate. because the rectangle goes over the area which you wish to estimate. If you look right here, you can see that right there, again, it's an overestimate, because the rectangle spills over the curve. It is possible to underestimate. I'm just going to draw that off on the side. If this is your curve, it looks like this. You could have a rectangle like this. Do you see how it's underestimating this stuff? It's supposed to be bigger, but it isn't. Yeah, we will be heading towards Riemann sums. I'm just sort of like, what's it called? Setting the intuitive understanding for what's going on here. So let's zoom back out. Okay, but the whole point here is what we're realizing is that the total estimated area is equal to the area of the first rectangle, which we'll call area 1, plus the area of the second rectangle, which we'll call area 2, plus the area of the third rectangle, which we'll call area 3, plus the area of the fourth rectangle, which we'll call area 4. Right? Each of those individual areas is an area of a rectangle. You need to add up all those different ones. Mm-hmm. You mean like this? So the thing is, I don't want to be at 250% because I want it to go all the way over to like the edge. I can like move around so you can see that. But I don't want to waste all of this stuff over here. Does that make sense? Because like what you wanted looks like this. And then I'm like wasting a lot of real estate. I don't like that. I don't want to like complain, but it just upsets me inside when I see that strip of my screen not being used. Oh, okay, cool. I get what you're saying. Cool. I thought you meant like in general, like for the rest of like. I was like, no, I'm sorry. I'm not going to be doing that. Yeah. Yes, exactly. Are mildly infuriating. Like I just can't deal with this. It won't let me erase that thing now. This happens to me, like it glitches sometimes. Okay, there we go. It fixed itself. Thank God. Okay, let me zoom back to the appropriate zoom. And by appropriate, I mean just the one that I like. And that's just like how everything will be decided here. Like, it's my preference and we're rolling with that. Okay, now here's the thing. For each of those individual areas, they are a rectangle. A rectangle. And each of those rectangles is a base times a height. A base times a height. A base times a height. A base times a height, right? And you start noticing that there's a repeated pattern here. And in fact, each of those bases is going to be what? Delta x. And what is each of those heights going to be determined by? Some x value, from the left or right endpoint on the partition that we came up with. So the first one could be called like delta x times f of x1. And the next one would be delta x plus f of x2. And the next one would be delta x times f of x3. And the last one could be delta x times f of x4. Where x1, x2, x3, and x4 are just those points that we came up with the partition on the interval. Now, mathematicians are lazy people. We don't want to keep on like writing the same damn thing over and over, especially if it repeats a pattern. So we have a quick, easy way to do this. We call it sigma notation. Right? If you ever want to add a bunch of stuff that follows a nice pattern, basically the whole point is that people, what's it called? When you do algorithmic processes like this, you don't want to have to write all of it out, right? You want a quick, compact way to write it. Sigma notation does that for you. That's why it was invented. So we would write this as a sigma The sigma tells you you're going to do repeated addition, and then what you do is you look at each of these individual things, and that tells you what your formula needs to look like. Each one of them has a delta x multiplied by an f of x something. Notice it's x1, x2, x3, x4, right? So instead of putting each of those numbers 1, 2, 3, 4, because it will depend, when you plug it in, you put a variable. So that's called the index variable. Okay, part of the sigma notation is explaining how the index variable works. So at the bottom, you write your index variable. We have an I, and you ask yourself, well, where did your index variable start? The first thing we plugged in was 1, so you put I equals 1. Notice then it went I equals 2, I equals 3. Hopefully you can see me circling it in red. The last one we put is I equals 4, so you have a 4 on top. These numbers, 1 and 4, they have a special name. We call them the upper bound. It's the last number that you plug in into the formula. All right, the upper bound, the last one we had was x4. And then the other one we call the lower bound. Just like how we talked about the bounds on the area. The lower bound was the 1 right there. Okay. So sigma notation, just in summary, is a way to express very succinctly the fact that you have some formula where you plug numbers in and then you keep on adding the things over and over from them. Okay, so we're going to talk now about the properties of sigma notation. Why are we doing this? Because eventually we'll use them in Riemann sums, but that's like a little ahead of us. If you already covered this in your 101A class, then you're like, you're probably feeling good. Okay, so let's talk about properties of sigma notation. My bad. So, let's say you have a sigma notation. Your index variable will be I, and I is going to start at 1 and it will end at some number n. And the only thing in your formula is a constant c. Okay, so what is this telling you to do? It's telling you to take your formula, and you're supposed to plug in I equals 1, but notice there's no I to plug that in anywhere, so you just get C. All right, you're like, plug in I equals 1 into my formula, there's no I, so you just get C. Then what's the next thing that you plug in? I equals 2. Once again, you just get C. You plug in I equals 3, and you just get C. And you keep plugging it in until I equals what? What's the last number that you would plug in? It's the final number. N, yes. Okay, so notice all you have is a bunch of C's added together. In fact, how many C's are being added together? There are n of them, right? Because you have I equals 1, I equals 2, I equals 3, all the way up to I equals n. Now, literally, if you have the same number added to itself n times, that is literally just the number times n. So what we get is a rule. If you have the sigma notation from 1 to n of a constant, that is just c times n. So let's give ourselves an example here. Let's use j instead of I. J equals 1 to 10, and then we're going to have 21 right here. This tells us that that's just going to be 21 times 10. which would be 210. Why? Because it is simply 21 added to itself 10 times. Right? And a number added to itself 10 times is quite simply the number times 10. Oof. Okay, cool. Let's go on to the next one. 2. I guess I'll go backwards this time. I'll give you a specific example, then I'll give you the general rule. Let's say you have I equals 1 to 10, and... Oh, you have a question, Mohammed? Mm-hmm. Mm-hmm. Yes, what I'm trying to say is there's another way you can think about this. The sigma notation is telling yourself 21, plug in I equals 1, 21, plug in I equals 2. Keep on doing that until you get 21, I equals 10, which is literally just 21 added to itself 10 times, which is 21. Yeah. Yeah, no, that makes sense. Mm-hmm. Just wanted to make like painfully clear to you that there's like two ways you can think about this, like and justify the behavior. There's the rule, and then you can imagine expanding it out, and then you should get the same thing. Yeah, exactly, yeah. Uh-huh. So you're just saying like if instead of this 10, you'd have a 2, yeah? 21 added to itself 2 times. Cool. Okay. Just move this down a little. Okay, so for this example, we have the sigma notation, I equals 1 to 10, and let's put 5 times I. So if we were to expand this, you would get 5, and then you would plug in I equals 1, so you get 5 times 1. Plus, and then you'd have 5 times, now you're going to plug in I equals 2, so 5 times 2. Plus 5 times, that's I equals 3, so you get 5 times 3. And I'm going to put dot, dot, dot. The last one is going to be 5 times, you'd be plugging in I equals 10, so you get 5 times 10. Okay, now just looking at all of this addition, what could you do to simplify and help more easily compute the answer? If you look at all of those terms, what do they all have in common? Boom, yeah. So what you could do is you could factor out the 5, right? You would get 5 times, and then you'd get a 1 plus a 2 plus a 3 plus dot, 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 10. Okay, so hopefully, is everyone sort of seeing that? The 5 times 1 plus 5 times 2 plus 5 times 3 plus dot, dot, dot plus 5 times 10. That is the same thing as 5 times bracket 1 plus 2 plus 3 plus dot, dot, dot plus 10. Okay, now what you realize here is that this stuff in the bracket, the 1 plus 2 plus 3 plus dot, 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 dot plus 10, that is a sigma where I equals 1 to 10 where you just have an I. Right? Like all of this right here inside of the bracket, that is equivalent to this sigma notation because it's literally just plugging in 1 through 10 into I. Now what do you notice happened? If you have a constant inside of the sigma notation, what can you basically do to that constant? Factor it out, just like how if you have a bunch of 5s in repeated addition, you can factor out all those 5s to right in front. That's literally what this rule is telling you. So you can factor out a constant in sigma notation. So in other words, the way you would write this is you would say if I have a sigma I equals 1 to n, and then you have a constant c times I, the c can be moved out in front of the sigma notation. Okay? So that's the general version of the rule. Constants can be factored out. Oof. Okay, that's a good place for us to stop and take a break. It is basically 12:50. We are going to break until 1:05. Cool. So I'll be back in a while.